Is this?
You are live now.
Is
If
this
you'd like
visible?
to go ahead.
Is this visible for you? Hello?
Yes.
Yes.
Okay, great. So should I get started or?
Yes, please.
Yes,
You're now
please. You're
live.
now live.
Okay. All right. Hi, everybody. Today on the Data Science Connect conference, we are going to go over gradient-based deep learning, and this will be a portion of a book that you can also access through xlibris.com. And today we're going to go through the deep learning architectures and neural networks to understand how it works and operates, and how do we apply the activation functions on the neural networks, and how do we apply the backprop and the forward pass to the neural networks. Tomorrow we're going to actually see it in a workshop where we can actually be able to implement it. But for tomorrow, please come with your Jupyter Notebook environment that you can actually try and run along with me for workshop session. That will be for tomorrow. But today we're going to actually go through to see and understand how we can implement this, and then we can actually implement tomorrow. So primarily, so this is a book that's available. It's in on xlibris.com, so you can go to xlibris.com and find this. If any particular topic we are going through today is not very clear for you, you can still read that from the book itself, and you'll be able to access the contents from there. So this is a brief background of mine where I've been working on the AI and machine learning and deep learning for some time, and the rest you can find in the book. Okay, so as we know that there have been tumultuous advances that deep learning and machine learning has brought to us, especially in the early 90s, that people have invented these neural network architectures, and we slowly transition from having those type of architectures where we had to write rule-based AI systems. So rule-based AI systems were always complicated because they would not really identify the issues in terms of okay, if it does not actually meet this requirement, how are we going to be able to implement it if there is no rule for it? For example, reinforcement learning is something AI learns on the fly, and if there is any particular incident that occurs in that environment, we will be able to pick up that and be able to actually convert that at a runtime, rather than rule-based system, which is going to be static and will not address all the scenarios that we would want the AI to address. So that's why the neural networks, even though reinforcement learning has laid the foundations for building the architecture for coming up with a runtime-based technique, but it could not come up with the other architecture where how do we actually process this, because especially when you have large-scale deep learning implementations, it's going to be very complicated in terms of going forward with the processing of all of the information through multiple layers and getting that into the outcome that we are looking for. So hence, deep learning has introduced a lot of neural networks, at least in the past 10 years, and that actually has incremented our way of processing large-scale information through the neural networks. And so ever since, most of the time, the AI system that you access, even just for you access your smartphone for speech recognition, you may have something like Siri. Siri helps you to find information for you, identifies your voice, and it translates it back to you in terms of the question you have. It's more like a Q&A based type of AI system. So how is it able to perform all of that? So because there are neural translation architectures underneath the city that performs this. And again, for processing any information of any scale, you primarily need to have the neural networks, which would be the like a feed forward information. So basically, you can build a neural network with thousands of processing nodes and millions of neurons that would actually work as a feed forward mechanism, and you also are able to perform this to process it and apply in a reinforcement learning environment or supervised or unsupervised environments. And you can also apply for various industries, whether it's retail or it's life sciences or it's healthcare or utilities, energy, any type of industry are all looking to implement such deep learning techniques with neural network implementations, and all of them you can implement. A lot of companies already have gone live on this type of scenarios where they're able to implement these techniques with neural networks. So primarily we need to identify, so we're going to take a simple example of a neural network here. I'll tell you how exactly you're able to operate and how do you process the information from input layer into the next layer, and then further how we're going to calculate the sums of each neuron with a summation formula, and then we get the output from each node, and then based on the associated weight and the resulting product, then you're going to calculate the threshold value, and you will pass the value to the next node, and so on and so forth. So that's how you're able to calculate your output based on your overall neural network. And the more number of neural network you have, the more efficient it becomes, but also it becomes more complicated because of you will have to handle any errors that occur whenever you perform this forward pass or backward pass in the neural network. So we're going to take a look at that to see how exactly we are able to implement that. Again, as we spoke about, deep learning is a subfield of machine learning. Machine learning is a hierarchical branch that has the AI. So it's like AI, machine learning, and then the deep learning. So the genesis of the deep learning primarily started with neural networks. And again, we have several types of neural networks that we can implement, like recurrent neural networks, convolutional neural networks, and deep belief neural networks. You also have Boltzmann machines and so on and so forth. Several types of neural networks that you have that you can actually implement in your architectures. And there are several innovatory deep learning models that are built based on generative adversarial networks and variational autoencoders. And you can apply to any field, as we spoke about, like whether it's a neural machine translation or natural language processing, or if you're running some autonomous vehicles, for example, for Tesla or a company like that, then you need to have machine vision so that you identify the objects that are in motion whenever the vehicle goes through the streets, and able to identify how to handle a scenario which is not something rule-based rather than a runtime scenario, which is what we're trying to get closer to mimic the human brain, where you have all of the ways to handle it at a runtime rather than like, okay, this is the rule and that's how exactly it's going to work. Or what if the rule, so there is a rule that's encountered which is not there in the system, then you can't really handle it. So that's why we try to get closer to the way the human brain works. And so again, autoencoders also is very popular, especially if you're applying it to the genomics, and you can, that will help you to, innovate and come up with new medicines, and can also identify, the patterns of the genes and how they actually work and what is causing a person to get a particular, type of illness. So you can take a look at that to see how we can apply there as well. So it is critical to understand how, why these architectures are the way that they are created today, because there's a way that's critical to understand for a lot of researchers that have been implementing in the recent times with restricted Boltzmann machines or deep belief neural networks, and so on and so forth. There are several, neural architectures that have spawned in the recent times, you can find papers getting released almost every month. You have tons of papers and you have tons of publications and conferences where people come up with their papers and come up with some concept on how they can even improve, for example, like a technique on a neural network, or how do you optimize it, or for example, like the gradient, how do you calculate it, how do you optimize it, how do you improve it? Because there are several number of optimization algorithms that also have been built, and more are getting built as we speak. But again, we still a lot of industries already have gone live on these neural networks that will require them to process large-scale hardware, and they'll be able to identify, how exactly we can leverage these packages and libraries to implement that. So, I mean, as I said earlier, tomorrow, I'm going to actually show how do we leverage this latest libraries and packages to implement with Python. How do we compute all of this, whatever we are talking about it today. You can see it in the workshop, but for today, I'm going to just go through the inner mechanics of back propagation, and we can understand how it works so that we are prepared for tomorrow's workshop, so that we can actually implement in Python, and also we can implement activation of activation functions with neural networks. So we can see how to do that. And again, you always can implement a backpropagation algorithm in either a PyTorch or a Python, or even you can implement in TensorFlow. It all, it varies with your situation as to how exactly, you're based on your organizational priority. Like if they say, okay, the PyTorch is the way to go, then you can implement in PyTorch or Python. Or if your organization, like you have a lot of Google Cloud Computing where you have installed TensorFlow, then you can also implement in TensorFlow with Google Colab notebooks. But for tomorrow, we're going to just be working on Jupyter Notebook. We can also take a look at Google Colab if you would like to, which also will allow us to connect to the GPU, and we can actually be able to run faster as opposed to Jupyter Notebook. You will not have that. You will just run purely on CPU. But to run on Colab, you will have a cloud-based GPU software for free, and we can run through that and see how we can see that. So as we can see here, so basically this is a simple neural network. So we have input layer, we have a hidden layer, and we have an output layer. So we also have a bias node created here, so that we can create some bias values surrounding it. So input neural network has A1, A2 are primarily your input neurons, and then you have hidden neural network layer, which is containing the Y1 and Y2 neurons, and then your output layer contains the Z1 and Z2 neurons. So you can activate these. So basically, we're going to assign some initial values, because you don't want to assign something that's arbitrary. You don't want to assign something with bias. So you want it to initialize with some values that would contain most optimized way, so that so we initially go and initialize this neural network to assign some weights. So for example, we are assigning the weights as weight 1, weight 2, weight 3, weight 4, weight 5, weight 6, and weight 7, so on and so forth. We are assigning weight for each of these neuron, and then we assign some initial weights to it. And also for the bias nodes, you can apply some computation of the total input and output values. So as I said, when we initialize, we need to be able to assign the weights in an optimized way, rather than just assigning it with fixed values that you are passing to it. So you want to apply with some sort of values that would be optimized there. So so here what we're trying to achieve is we're going to try and take the compute, the net input. So net input is basically y1, which is in the hidden layer. So you have a neuron there, and then you also have net input y2, which is another intermediate computing layer, in the hidden layer. You get that information processing from each weight. So as you can see here, so you have weight 1, weight 2, weight 3. So these are the weights for each of the neurons. So we're going to apply the summation to see how it works. So the way that we calculate this summation is with the net input y1 is going to be basically your weight 1 multiplied by the neuron, input neuron value plus, again, we go for weight 2, and that's connecting the node here. And we multiply that by A2 value, then we're going to multiply with the bias and the value for the bias, which is the one we have created here. So that will give you the total net input value in your hidden layer for y1, and then you also want to compute the net input value for y2 as well. And that will give you, again, similarly as we spoke, in this case, we're going to take weight 3 and weight 4 here. And then again, we multiply with A1 and A2, which are the input neurons, and multiply with our bias node. That will give us the net input value for the hidden layer neurons. So again, we can apply the logistic function. So we can see what are the various functions, activation functions. For example, like we have sigmoid, we have logistic function, and we have several types of activation functions we can leverage. And I will show you tomorrow how to activate. But for now, we're going to assume that we're going to be able to apply an activation function and activate a neuron so that a neuron is active, and then you will get your output computed. And so if you apply the logistic function, and that will give you the output. And so basically, we're going to apply this to A1 and A2 output layer, and then we compute the neural networks. And so here you can see how we are computing with the logistic function, we are activating this particular neuron. And this is the calculus formula for computing the error for each neuron. Whenever we perform a calculation, there is a room that we could have some potential error. So, the net input Z2 is basically what we are computing here, and that is going to be net input Z2. So we're going to take the weight 7 we saw earlier, and then multiply that by net output A1. And plus W8 multiplied by net output A2, and then we compute the bias. And if you add all of that, that will give you the net input Z2. So that's what your net input Z2 is. So now again, when we see this calculation process, so we want to calculate the error. So our objective here is in a neural network, when you compute a back prop or a forward prop, you want to reduce the error that you have so that you're going to be able to get a handle on the situation, and you will have a very optimum output in your neural network. So whenever you're passing it, whether it's going to be for computation of chemistry or quantum computing, or it's going to be for your retail industry, regardless, you want to minimize the error as much as you can so that your computation accuracy is higher when you actually implement this type of neural network. And again, when the error is minimized, you'll have a higher accuracy for neural machine translation or any particular task, whether it's going to be an autonomous vehicle, so it's going to be able to react in time and evade any situations where, collisions with pedestrians or so on and so forth. So that's why you would want to minimize your error when you compute your outcome, because that is exactly how you're gonna make a call. How you want to react in that particular situation, or how it's gonna branch to the next step of a logical step. So you will understand that. So basically here we're just computing this with a chain rule. And how exactly are you going to be able to compute a chain rule? So in calculus, it is, you want to simply differentiate a function of a function. So for that, we are creating a f of z. So we are simply differentiating a function, which is cos z of z is z squared. So f of z, which is a function of a function, will give you f cos z and cos z squared. So we are simply differentiating a function of a function here. And because we want to find that dx by dz, and then you're going to consider the substitute as y as z of z, and then we can apply the chain rule with it, which is and again, if you want to understand the basics of calculus, which is also very critical for working on the neural networks, and you want to understand the linear algebra, also critical for understanding and implementation of that. There are separate chapters allocated in the book for going through the basics of linear algebra and calculus, so that you are equipped and you are ready before you actually start going through a neural network architecture, and later you actually implement backprop or a forward pass through Python or PyTorch or TensorFlow, so it will get you equipped for all of your implementations. And so that's how you can actually be able to be prepared for such implementation. So please go through that tomorrow. If not here, or take a free tutorial. You have plenty of free tutorial software, and you can go through the free tutorials and try and understand how you can actually be able to implement a simple chain rule, or you want to implement linear algebra. So for example, you want to implement matrices. So you can compute a matrix, you can get a product of a matrix, and so on and so forth. So you can perform some simple calculations on computing the matrices, and you will be able to and then be prepared for going for any such differentiation calculus formulas that you want to implement for so on and so forth, such as, for example, automatic differentiation is another type of calculus way of implementing. Now in PyTorch, you also have a package and library provided for you that will actually help you to implement the auto differentiation. And so that is something that you can actually implement in your PyTorch. So in Python, when we used to work earlier, like almost 10 years ago, it was very tough because there are not any bundled packages or functions or anything that's available. You have to compute everything manually, whether it's going to be a chain rule, whether it's going to be a automatic differentiation or any formula, you have to compute it now. But there are some things that you can actually leverage when you come to PyTorch and TensorFlow, because they put in efforts to actually build those functions for you. And so you can simply implement those functions in Google Colab or Jupyter Notebook, wherever your enterprise environment is, and then you will be able to actually minimize your codes and efforts, because it's going to be simple and intuitive in terms of actually be able to implement those functions through the calculus with packages in PyTorch and TensorFlow. But again, for tomorrow, we're gonna do this in an old-fashioned way for the workshop. We're gonna actually be able to implement this in Python. Everything is going to be manual calculation completely. There's going to be no leverage of any PyTorch or TensorFlow type of built-in packages we're going to leverage. So when you understand the concept, when you compute everything manually, it's going to be easier for you to be able to actually implement this in any other programming language. As you understand the concepts and of linear algebra and calculus and neural networks, then you can implement it in any programming language, which would not be an issue. So here we're gonna compute the backprop with chain rule. So we're gonna compute so this is a formula we also saw earlier in the slide, where we're trying to compute this for each of the total, for the gradient. And so you can compute this by target and for each output. And so if you apply all of this, then so you're going to be able to compute this and the output value for the neural network. And that is what is going to give you the, your output. So again, we're going to actually see this. We're going to take some sort of a toy data set tomorrow. We'll take the toy data set, and then we will actually be able to implement this in Python so that you can see how we actually cluster the information, and we pass this through the neural networks and compute this, and how do we apply the chain rule, and then so on and so forth. And then you can see the outcome from the Python. You know, and also, like, if you have any other questions, you can feel free to just get in touch with me on LinkedIn. I'm always available. So for any questions or any further clarifications, feel free to get that. And also, as I said, like, you can also get the book from excelbliss.com. And again, when you have questions, it's whether it's part of the book or not, feel free to reach out for any of your internship projects you're working on, or you're working as an advanced data scientist and you're trying to solve a complex conundrum at your organization, and you run into some sort of a situation. Feel free to reach out. I'm happy to provide the insights for you. But tomorrow we're going to actually go through the workshop to see how we can actually implement this. Yeah, any questions you have, please feel free to come up with any questions.